Okay, so today we're going to solve linear systems by multiplying first. Okay, so guys are wasting my precious recording time right here. We are solving systems by multiplying first. So what system did we learn to use yesterday for solving linear systems? What method did we learn, everyone?
Addition and subtraction.
No, it's called, it begins with an E. Elimination. So what is the goal of elimination? Why do we use elimination in solving a system of equations? Kathleen? Very good. So we can isolate a variable. So today we are going to have to multiply first in order to eliminate a variable from a system. For elimination, we need opposite or identical terms. If we have opposite terms, what operation will we use to eliminate? If we have opposite terms, the operation we use is addition, right? If we have same terms in the system, the operation we use is subtraction. Good. And that's why we need opposite or identical terms. So today we are going to multiply one or both equations by a constant term to create opposite or same terms. So in this first example, we are going to multiply just one equation by some constant in order to create opposite or same terms in the system. So which equation might we blow up? Really, we're finding an equivalent equation, right? In order to have opposite or same terms. Carrie?
Multiply the top equation by 2.
Carrie says multiply the top equation by 2. If we multiply the top equation by 2, will we have opposite terms or same terms? We'll have same terms. So what operation will we use then? Subtraction. Okay, so we're going to try Carrie's idea here. We're going to multiply the top equation by 2. So let's go ahead and rewrite the equation. Abby?
Did you also multiply it by -2?
Thumbs up if you think you could multiply this by -2 as well. Yes, and I love that idea because I love opposites. So go ahead and try it. But we're going to show on the sample here that we're multiplying by 2 to get same coefficients. So we have 4x plus 2y equals -18. And we do not need to change the second equation. We have 4x plus 11y equals 9. So now we will subtract the second equation from the first. When we do, we need to remember that we are going to add the opposite. Right, we're going to add the opposite of each term. So I'm distributing the negative. Add the opposite, opposite, opposite. So 4x minus 4x eliminates the x term. So we'll cross that out. 2y plus a -11y is -9y. Good. And -18 plus -9 is -27. Okay? So we simply isolate y by dividing, and y equals 3. Good. We're going to bring the 3 over and substitute into either equation. We could even substitute it into the blown up equation, the equivalent equation. It doesn't matter. This value of 3 has to be true in all the equations of the system. So which equation would you like to substitute the 3 into? Alyssa? Okay, the first equation. So we'll go 2x plus 3 equals -9. This is the y. We found it is 3. So the next step is to
Subtract 3.
subtract 3. 2x equals -12. Good. And finally, we divide by 2. And x equals? -6. Good. X equals -6, which we can write as an ordered pair. Now don't forget to mentally check at least, or go ahead and write it down. Is it true that negative 6 times 2 plus 3 equals negative 9?
Yes.
Good. And is it true that if we plug negative 6 into here, so 4 times negative 6 plus 11 times 3 is 9? Is that true too? Yes, so we can check off that we know that this is the solution. Just a second. Okay, so in this example, we have a few things going on. What is the first thing you see? What's the first thing you notice here, Carrie?
The equations aren't linked up.
Very good. So we are going to have to rearrange one or both equations so that we have our like terms in columns and our equal signs in columns too. So how would you rearrange the second equation so that it looks like the first? What would we do? Amaya.
Add 7x to the side.
Okay, so she says if we add 7x to both sides, we can end up with, tell me what you have.
7x plus 4y.
Okay, so when we put the first equation in place, 2x minus 3y equals 6, we now have like terms in columns. Okay, so very good. We now look at it and say, do we have opposite terms or do we have same terms? Are the x terms opposite or same? No. Are the y terms opposite or same? They are? Do we have? We don't? No, we don't. Negative 3y and positive 4y? They are not opposite. They're not the same. So what can we say about these numbers? Molly?
Well, you could multiply the second equation by 3 and the top equation by 4 and have the same outcome.
Okay, so Molly is suggesting that we multiply the top equation by 4 and the second equation by 3. So which term, x or y, is Molly creating opposites for? Everyone?
Y.
Why? So she noticed that the least common multiple of 3 and 4 is 12. So she's trying to create opposites for the y. Make them both 12. 12 and negative 12. So that's great. What else could we have done here? Joey?
Multiply the bottom equation by 2 and the top equation by 7.
Okay, so he said multiply the bottom equation by 2 and the top by 7 so that x's would then be the same coefficient. We could then subtract. So either method is fine. We're just trying to eliminate one variable. So let's rewrite the equations. Transformed so that they have, in this case, opposite coefficients. So we end up with 8x minus 12y equals 24. And here we have 21x plus 12y equals negative 24. Ends up being a really easy system, doesn't it? Because when we add these two together, we end up with 29x. The y terms have been eliminated. And what is 24 minus 24?
0.
0. It is 0. So when we divide by 29, x equals 0, which we can bring over here to substitute. And where would you like to substitute this 0? Alyssa?
The top.
Top one? Okay. So we end up with 2 times 0 minus 3y equals 6. So negative 3y equals 6. So everybody tell me, what is y equal?
Negative 2.
Very good, negative 2. Again, write it as an ordered pair. I'm squeezing this in the box, but write it as an ordered pair. And let's test the equations to make sure it's true. So is 2 times 0 minus 3 times negative 2 equal to 6?
Yes.
Good. And is 4 times negative 2 equal to negative 7 times 0 minus 8?
Yes.
Yes, it's true.
Okay, well, I'm going to multiply this,
You want to multiply the first equation?
yeah, the second equation
Second equation?
by 3
Oh,
He's multiplying the second equation by 3. Okay, so the one thing we might do is move it over here. Can I grab it and move it over here? Okay, and that will make it easier to line up the equations, right? So now he's just rewriting the first equation.
And then I'm going to add them.
He's adding the equations. And yay, he has opposite coefficients.
And I'm going to divide by 7.
Very good. So he's got y equals -2. Thumbs up if you agree. Y equals -2. Good.
And then I'm going to plug it into the second equation.
Thumbs up if you agree. X equals -1/2. Okay, and so give us your solution. And let's just do a quick check. -1/2 times 6 is -3. -2 times -2, which would be +4, right? -3 plus 4 is 1. And we have -2 times -1/2 is what? -2 times -1/2 is 1. Good. Plus 3 times -2 is -6. 1 plus -6 is -5. Woohoo! Gotta say your woohoo, Preston.
Woohoo!
Yeah. Okay, so we have now learned all of the methods for solving a linear system. So we're going to just make a box here and jot them down as a review. To summarize what we've learned, there are actually 4 methods for solving linear systems. This first method is one that you just did a quick little, they reference it way back at the beginning of the chapter, and we didn't put much down, so I'm going to show you a sample of it right now. If I give you a table, actually in this case you can see I've given you 2 tables. These 2 tables are representing 2 linear equations. And we know that. How do you know that? How do you know that these 2 tables represent linear equations? Kathleen?
Because with the x and y, on 1 and 0.
Oh, no, you're getting ahead of yourself. If we look at these tables, how do we know that these are just linear equations? Jack?
I don't know what it's called, but there are solutions for
No. Preston?
For every input, there's an output.
For every input, there's an output. And do you see a pattern in the x, the inputs here, in the domain? There's an increase of what?
1.
1 every time. And what's the increase in the y?
5.
Every single time. We're adding 5. That tells us we have a linear equation. Now in the second equation, we have increases of 1, again, in our domain. What is the increase in our range? 2 every time. So again, we know it's linear. So how would we solve this system? Do we need to graph it? No, we're going to do what Kathleen was going to tell us, which is, what's the solution of the system here?
Well, I put 1 and 0.
She says 1, 0, why 1, 0?
Because it's on both of them.
Because it's in both. You can see this, that point exists on both of these lines, right? So do you need to go graph it? No. You could you go graph it? Yes, but you don't need to. There it is.
There.
The answer is in front of your eyes. So that's called using a table to find a common point of a system. Now there's only so many times you can practice that, because once you've done it once, you're going to do it every time just like that. You see the common point if given a table for each line. Okay? But really, what was the first method that we spent tons of time on? Alyssa? Graphing. And so, do you love graphing? Who loves graphing? Let's hear a hooray for those who love graphing. Nobody. Oh, Gracie loves graphing. Oh, no, she doesn't. Okay. So, when do we use graphing? I say if desperate. Use graphing if desperate, or if you are commanded to do so. You must graph. But really, we probably prefer using our algebraic methods. Which was the first we learned? Preston?
Elimination.
No, that wasn't the first one. That was the last.